Thank you.
Thanks, John. Thank you very much for the nice introduction. And one thing I want to mention that though, this is a different piece of work. It's from that project, but different from the one I presented previously. This is actually the first time we try to present for this specific piece and collect feedback from stakeholders. So thank you again, John, for inviting me, and thank you everyone for joining the webinar today. I'm very excited to share this piece of collaborative work on forecasting peatland changes on the different scenarios in Alberta. This is co-authored with Wang Hongyu, Vic Adamovich, David Olifield, and Brent Swallow. And please move to the next slide. So here's what I will cover. I'll introduce the project and our team very briefly first, then provide some background context why forecasting peatlands are important, and then walk through our methods, data, and preliminary key results, and end up with a brief policy discussion. So that's the plan. Next slide, please. So this specific work is part of the project Modeling Peatland Disturbance and Conversion in Alberta, Understanding Baselines, funded by Environment and Climate Change Canada, ECCC, through the Nature Smart Climate Solutions Fund. The main or the key project goal is to try to establish dynamic baselines for peatland disturbances and loss here in Alberta. We also try to have a good understanding of the current state of peatlands here and identify and assess those key sources of disturbances, focusing on human-induced activities like energy development and agricultural expansion. Beyond that, we are also doing a couple of other related things. I can share more if time permits at the end. So this project, we have 4 investigators with very, different background, different areas of expertise. Vic brings expertise in resource and environmental economics. Brent is an expert in policy analysis. David is a leading peatland ecologist. Myself, I am an economist who's very interested in quantitative analysis, land use modeling. So that's us. And we are also very fortunate to have a dedicated HQP team. I'm not going to introduce all of them. And I want to mention one specific graduate student, Hongyu Wang, who did a majority of the empirical work for this piece. Okay, next. So that's the team and the project. Next, I'm going to provide some context, background information about why peatland is so important. So peatlands are a special type of wetland, and they provide vital ecosystem services. They are very important in water regulation, for example, reduce flood risks. And also they are very important in supporting biodiversity, provide a habitat for those important unique species, wetland species, plant species, animal species. And for many First Nation communities, peatlands are also important in provide spiritual and cultural values, benefits. Peatlands are also harvesting places for their traditional medicines. But other than that, here, probably the most critical reason we're talking about the peatland here today is their climate regulation function. So peatlands, although we only have about 3% of peatland, I mean, in terms of the land base, 3% of the Earth's land base. However, they stored about or over 30% of the soil carbon. So they are really like critical in terms of the climate regulation and dealing with the climate risks. So that's the unique part of peatland. But this peatland, this carbon vault is fragile. Once peatlands got fragmented, got disturbed, burned, or drained, this carbon sink potentially can become carbon emitter, and they might become, or quite likely will become, sources of substantial greenhouse gases. So that's why when losing peatland, it's not just we're losing wetland, we are also releasing a very powerful climate risk. So, and here this map shows presents the spatial distribution of peatland, the probability of spatial distribution of peatland in Canada. And you can see in the western area, Alberta has also lots of peatland concentrated in the northern part, the boreal forest region, green area. Okay, next, please, slide. So that's a big picture peatland in Canada. But what makes Alberta unique or so special in terms of peatland, or when it comes to peatland? Alberta is one of the, I guess, the most peat-rich provinces. So peatland counts 14 to 16% of our land base in total. So we are big in terms of the total quantity we have. But other than the quantity, we are also in a very unique place in terms of the peatland, because these peatlands, if you look at this map, oh well, I cannot really use a laser point. So if you check Alberta map, and you will see in the northern part, those peatland concentrated area, these peatland almost very perfectly overlaid with some of the world's largest oil sand reserves. Places like the Peace Rivers, the Peace River, the Cold Lake, Athabasca. So these are the big oil sand reserves. And there are lots of energy activities, open pit mining, for example, and pipelines construction, in-situ bitumen extraction, lots of well sites. So these are all disturbing our peatland, and will have important, of course, carbon and other implications. So that's why this is very important in Alberta. We are rich, but we also facing these challenges. And compared to other provinces, other peatlands, maybe you can imagine it will be potentially more expensive to conserve peatland if peatlands competing with these resource uses industries, right? Not just the energy industries. And here we also, in the past, let's say several decades, we also see agricultural, quite aggressive agricultural expansion along the forest and prairie line, the transition zone. So basically transition zone between green and white areas. We see some substantial losses of peatland due to crop or pasture or grazing areas expansion. And these are often like once peatland got drained, it's very hard, almost impossible to reverse back, impossible without a super expensive intervention. So yes, Alberta has lots of peatland, but we are also relying on these critical industries that threaten them. It's probably won't be feasible, economically feasible to protect each hectare of peatland in Alberta. So the question is, what's feasible? What can we do in Alberta if we want to contribute, or if we want to contribute meaningfully to the climate goal, utilizing this very important ecosystem peatlands? Okay, so next page. It's a big question. To answer this question, I guess it requires lots of different information and needs lots of work, and like across different dimensions: policy, economic, ecological, spatial, lots of things. Our team tried to contribute to this broader question as well by first have a good understanding of the current states, and also potentially what would change in the future based on different situation, different conditions, different scenarios. And that's why we want to do forecast for this project. Why forecast? Forecast is important. We need a forecasting, so forecast can help us plan ahead to have a good or relatively good understanding what if situations plan in advance. And also most importantly, this kind of forecasting can also provide a counterfactual baseline later on when we have specific policies or specific projects, like project to conserve peatland, projects try to incorporate the carbon value into the peatland management. We can do comparison to evaluate, to assess the effectiveness of these projects or these policies. So we can compare the future peatland change versus the forecasted future. Then we can comment more, draw some conclusions regarding the effectiveness, efficiency of the project, of the policy. So that's why this is so important, not just an empirical exercise. It will support evidence-based decision making. Okay, next. And several, or mainly 3 gaps in existing research. So the first one is, so when it talks about their peatland disturbance literature or peatland, loss of peatland literature, we see most of those literature focus on the, like, try to assess the current situation and investigate what already happened, the past situation. And not many studies actually focus on forecasting future. One big reason why we don't see lots of future forecasting kind of work is because of usually we lack of the reliable and consistent that can allow you to do the temporal comparison peatland data set. So because of the data limitation, we don't really see lots of forecasting work. As you can imagine, forecasting the future will need to link to what happened in the past, link to examine the past change. You want to check the past change, you need to have not just a snapshot of the data, you need to have panel data, time series data. So that's one thing. And the second thing, usually when researchers, including our team, assess in another piece, assess the disturbance, we focus on the directly disturbed area. For example, how many square kilometers got disturbed or already been lost due to, for example, agricultural expansion, due to road construction, due to infrastructure. So a very quick dirty tip would be you overlay with the historical, maybe the peatland data or current peatland data with those human activities, and you can see the overlaps. You can calculate the current overlaps, and you can calculate the historical overlaps, and you can kind of comment on how many peatland, the total areas got lost due to a specific type of disturbance. However, this way, we do this as well, but this way will very largely underestimate the actual impact from human activities, right? Beyond the direct physical like overlap between the two, peatland and the human footprint, there will be more impact, indirect impact, human activity impact on, for example, the overall, if it's extensive, overall peatland ecosystem in the nearby area, will affect the surface, for example, vegetation layers, will affect the water table, will affect the hydrological function, a lot of things. So a more comprehensive assessment of the impact will require also check these indirect impacts as well. So that's a second limitation in the literature. Like I said, it's including our own team. It's a common practice, but it will overlook the total impact. But I mean, meanwhile, it's very hard to really quantify the indirect impacts. And the third limitation is related to the second one. So when we say loss of peatland or peatland disturbance, we tended to focus on those major like human footprint, energy activity in our case. In other provinces, for example, peat extraction for horticulture and the forest and ag general impacts. So we tended to focus on these specific sources of disturbances. We don't really pay much or like sufficient attention to the I guess transition from peatland to those natural looking landscape, for example, peatland to other types of wetland, peatland to grassland. But many of these actually reflecting the long-term indirect impacts from these human activities, from these human footprint, or from like a specific disturbance, including wildfire, not necessarily human related, but related to specific disturbances, but beyond that, longer, broader impacts. So are reflected in these transitions, transition from peatland to other, looks like natural, but not necessarily actual natural transition type. Okay, so next page, please. Okay, so for our research, we try to address two of these gaps partially. So first, we try to create our own peatland panel data or time series data. So we created a peatland data set for 2000, 2010, and 2020 periods, utilizing existing inventories, not created the raw sources of data, but utilizing the existing data, created three snapshot for 3 different periods. And we also try to investigate and forecast land use change, not just land use change of peatland to human-related activities or human-related land type like cropland or built-up area. We try to investigate the whole picture, all the transitions between peatland together with other land. And we do the forecasting on the 3 different scenarios: business as usual or natural progression, and then ecological protection, and then the accelerated energy development scenarios. I will say more about these scenarios when we talk about the results. And we also, for the we also want to discuss policy implications and potential policy limitations within the current existing framework. Okay, next, please. Okay, so in terms of the modeling, so here is the modeling. The model part includes 3 components, or include 3 steps. In the first step, we can do the first row. So we try to utilize the two biggest existing peatland inventory in Alberta, utilize these, combine these together to create a possible potential extended peatland area potential. And then we try to overlap this potential peatland area, not the actual peatland area potential, given the data we have, then to overlap with 3 periods of land cover data, global land cover data, and in order to create 3 pieces of peatland information for 3 different periods. So we overlap the potential peatland area together with 2000 land cover data. Then we can remove those areas, obviously not a peatland. For example, we overlap the potential peatland layer together with 2000 land cover, and we identify those areas labeled as peatland, but they're actually in 2000 already become, for example, roads, built up areas. So we remove these obvious non-peatland areas. So basically they are roads, they are, sorry, not the roads, they are built up areas, unutilized land and water, and yeah, basically cropland, agricultural uses. These are the major ones. And then the rest of the potential layer becomes the 2000 peatland database. And we did that for 2010 and 2020 as well. Then we have the 3 land cover. We have the 3 land cover data, which includes the peatland land cover information. That's the first step. And then the second step, we try to find the potential drivers drive the land use change from, for example, geophysical aspect and social economic aspect, climate aspect. So we collect the relevant information and use them later on for training the random forest land use model. And the final step so involves actually the modeling. We use the PLUS model, patch level land use simulation model. And based on the 2 sets of data set, we get ready. So the land cover data, 3 periods. So 2 periods changes. And the matching, lots of potential input features, X variables, you can interpret in that way. And then do the modeling. So the modeling involves actually the 3 components, 3 parts. First, the Markov train will use the Markov train will give us the estimated land transition probabilities for the entire study area, for the entire province. And then the second step, random forest. So we'll try to model at the cell level, linking the land use change to these potential drivers for different land use change. Each land use change will train 1 model, and then we'll produce a cell level probability or suitability for specific land use change. And then the final step, refine the probability or suitability or growth probability map from random forest by introducing the neighbor impacts and a couple of other controls in the final CA modular. And then based on the CA results, we have a more refined cell level, refined suitability or probability for land use change, then combined with the land use transition matrix we obtained from the Markov train model, and we can calculate for each cell for the entire province, the land use change. And we focus on peatland related land use change on the 3 scenarios again. Next. And here the data, so the 2 peatland inventory data we utilize, we use to create the potential peatland layer first, the ABMI wetland inventory data. This represents the most, I guess, recent and most consistent peatland data we have in Alberta. It's 10-meter resolution, and based on the remote sensing imagery obtained in 2017 and 18, the process utilized very consistent classification mapping technology. This is independently done by ABM Alberta Biodiversity Monitoring Institute. So the technique is pretty consistent, which allows you to do comparison in different areas across the entire province. That's, I guess, the best part of this data set. But meanwhile, this is, again, a snapshot and only reflect the best knowledge, I guess, representing the peatland state in 2018 and 17 and 18. Then next, the Alberta merged wetland inventory. It's a composite of many, like 35 different wetland inventories putting all together. So as you can imagine, I guess the quality, the resolution, the data sources as well will vary by region because it's not a consistently processed. It's obtained from different sources. But meanwhile, some areas will have very high accuracy with high accuracy and high resolution, and has done a bunch of like really good site cross validation, which is kind of a shortcoming in the ABMI data set because ABMI did not really relying on any site cross validation. So there are, I guess, trade-offs between these two data sets. And we put them all together, try to create the boundary of possible potential peatland here in Alberta from, for example, 1998 to most recent, then overlap again this with land cover data, create our own peatland data set. And by the way, we are using the 2021 merged data set, but they do have a new or updated version released this year, I think, with more recent information, and especially the missing area, the Wood Buffalo National Park originally was missing from the merged data set, but now they have information covering this area. Okay, next page, please. Okay, so this shows the relevant input feature we collected. So we have lots of information, the elevation, slope, pH value, top organic carbon, temperature, precipitation, infrastructures, and we also calculate distance to infrastructures, and also the coverage of well sites and mine areas and so on. These are potential factors, drivers might impact the land use change. Next, and yeah, this lower table shows the data source and the link. Yeah, next and next. So here are some preliminary results. So first, the data set. So this is ABC. The data set we processed based on the approach I just mentioned. So we have land cover data for 2000, 2010, and 2020, and peatland becomes one class in this processed data sets. So based on this, we can do more land use change analysis and land forecasting, land cover change forecasting. And based on the 3 data set we have here, so we checked the historical change of peatland. So as you can see, from 2000 to 2010, it's very hard to like visually inspect. So don't try to do that. So based on the number, we lost only tiny, very mild amount of peatland in the first 10 years. But if we check the 20 years, like from 2000 to 2020, we see about 1,400 square kilometers peatland loss in the past 20 years, which is about 1.6% of the peatland base, which seems to, I guess, seems consistent to our other pieces of work and to the literature and expert opinion as well. So that's the quick check of the general change using the historical data. Next, let's take a look at scenarios. Before we can look closer about the future changes, forecasted future change on the different scenarios, I guess better to talk about the scenario themselves first. So we have 3 different scenarios: business as usual or natural progression, which basically means we follow the trend land use change or land cover change trend will mimic the historical one. So the one from 2000 to 2020, if we don't impose any specific like extra protections, or we don't accelerate the development, just follow the historical pace. That's the first assumption, the scenario. You can consider this as business as usual. This will serve as like a basic or baseline we can compare with other scenario. And the second scenario is the ecological protection scenario. So in this scenario, we try to conserve peatland and wetland, overall speaking, the wetland ecosystems, and we also value the biodiversity and the hydrological functions of these lands. So we imposed here the third and fourth bullet points, these constraints. So peatland and other wetland, we restrict the loss of peatland and wetland to built up areas or cropland or unutilized land by 80%. And we also reduce the possibility of forest, shrub, and grassland to these human activities also by 50%. So cropland and built up areas, 50%. And water body, converting water body to built up cropland by 60%. Meanwhile, we want to also allow land reclamation or restoration effort. So we assume the cropland and the grassland back to, cropland and grassland back to peatland by 20%. This is a typo. So back to peatland, 20%. So that's the assumption for this ecological protection. Next page, please. And for the accelerated energy development, so we try to mimic or try to simulate the degradation, both direct impact of these accelerated human activities on peatland and other natural land, and also the indirect, for example, the drainage, the drainage impact on potentially like a change of peatland or switching of peatland to grassland and to shrubland. So based on the literature, so we impose this kind of indirect degradation, ecosystem degradation as well. And the specific assumptions are on the next page, please. So specific assumptions, we allow the conversion of peatland, grassland, shrubland to built up areas increase by 60%. And also the forest, shrub, grassland to unused land, those land, for example, initially a natural landscape, then due to industrial economic activities, for example, open pit mining, and remove all the surface vegetation. So this bare soil can be a type of unused land. So this is just an example. So we increase the possibility of forest, shrub, grassland to unused land by 40%. peatland to grassland by 60%, and peatland to other wetland by 50%, and peatland to unused land 20%, and grassland and shrubland to unused land by 30 and 20 respectively. And these are the main assumptions. And also we allow, to be more realistic, we allow 20% of land reclamation post try to I guess mimic the post disturbance land reclamation situation. So we allow the built up area to get back to grassland by 20%. Okay, so that's the scenarios. Based on these scenarios, here are the results related to the peatland change. So the first two bars again are the historical ones, and the next three are the next 10 years forecast, and then the last three are 20 years forecast, so representing the 2040 situation. So you can see projected loss in the next 10 years, so up to 2030, are modest, relatively modest. We only see a little bit loss, so 3% or close, like 2.4 to 3% compared to the 2000 level for the first two scenario, and a little bit more for the last, the accelerated energy development scenario, 5%. So these are relatively modest, but if we check the longer term, 20 years, the loss become more significant. So reflect the business as usual, we will lose 8.4% compared to the 2000 level, or 6 point something compared to the 2020 current most recent state. And for the economic development scenario, it's very dramatic. As you can see, it shrink a lot. I think 15% compared to the 2000 level, the total loss of peatland due to lots of things, accelerated energy development caused direct and indirect losses. So these are the general numbers we can see from here. In the short term, so peatland loss is not a linear like a progress. It's much faster than linear. First 10 years, this, and the next 10 years, not just the first year times 2, much more than the first year times first 10 year times 2. It's, I think, I guess, consistent with the peatland characteristics. Losing peat layers won't happen in several years. It's reflecting a longer term, like cumulative effects. It takes maybe 20, 30, 50 years to gradually decompose, and especially if we're talking about those very thick peat layers, not just 40 centimeter layers. So yeah, next page, please. So this gives us some big picture. And next page here, this gives us some details regarding the transition, regarding the net loss of peatland to different types. So from this graph, from the graph on the right-hand side, we can see first, again, 20 years loss is moderate, 10 years is moderate, 20 years is significant. And a couple of, I guess, interesting findings. Built up areas itself, the human footprint built up areas itself is pretty minor across all scenarios, across different time lines, the 10-year, 20-year. Overall speaking, the minor built up areas are minor, except the last one, the accelerated energy development scenario. Overall speaking, the majority of loss has nothing to do with the direct built up areas. And so that's one thing. And the second thing is the cropland conversion. Overall speaking, different from like other natural land cases. So for the cropland conversion, different scenarios, different periods tend to be pretty consistent. Under all scenarios, we see a loss of peatland to cropland somewhere between 200 to 500. 10 years, 10 years, we see around 200, and 20 years, 300, 400, or close to 500. So that's pretty consistent and pretty robust, which also makes sense because the cropland conversion only occur, the predicted area, or the reality as well, one occur everywhere. We are talking about the northern area, so most of the crop expansion are along the white-green transition area, the line. So that's this. Then, other than these two, for the natural progression scenario, so we see peatland loss to different categories, different types of lands, natural lands. Some are potentially misclassification, as you can imagine. These remote sensing stuff always comes with errors, but some reflect potentially true change of peatland, maybe accumulated from a long time ago, not just the past next 10 or 20 years. Decomposition starts earlier, but we observe or detect the final change, the change in the classification in 10 or 20 or longer year window. So we see the loss of peatland to different land type.
And I'm just interrupt, maybe 2 minutes left, if that's all right.
Sure.
Thank you.
And for the environmental protection, and although it's environmental protection, but we only see tiny little, very minor reduce of the loss of peatland. We still see quite a substantial loss of peatland, but to different types. For example, loss of peatland, loss to shrubland. And for the economic, for the accelerated energy development scenario, you can see it's very massive loss of peatland. Next page, please. And so these are the results. So we are still in the process of trying to draw conclusion, trying to try different scenario, different definition of scenarios to see the sensitivity and robustness, and try different model specifications and try to draw conclusion regarding the carbon implications. But other than that, a little bit about the policy, wrap up policy implications. So I guess policy is a very complex topic when it comes to the peatland. The peatland management will involve not just the land policy, it's also water policy, policies related to water, to energy sector, and to land, water, energy. So it's complex, and I think Bran and Julia will provide a more comprehensive assessment and discussion related to the policy. Here, maybe a little bit about the specific point, utilizing, for example, Alberta's wetland policy as a tool to protect peatland here. Is that sufficient? The short answer is maybe not, because this is not a peatland specific. The biggest problem or the biggest limitation is this policy does not really take into the consideration of carbon storage value of peatland, and does not really consider the longer term, for example, long-term restoration time window into the monitoring or reclamation mechanism. So the current relative wetland value system do value the biodiversity, human use, water regulation, but didn't really put value on the climate regulation side, the carbon storage side. This may be one thing potentially can be improved or can be like discussed for future. Next slide, please. Last slides. The future improvement, and maybe we are considering, we understand I guess our understanding is it's not quite likely for the province to develop a specific peatland policy in addition to this wetland policy, but potentially maybe there's room for a sub-frame under this big umbrella, try to incorporate those specific features, especially the carbon storage benefits into the valuation system and into the monitoring and compensation system. So that's this. But again, there will be more comprehensive, complete discussion from Brent and Julia in the next webinar. Okay, thank you very much. Yeah, I will skip the conclusion remarks, and I'm happy to answer questions.
Great. Thank you so much, Feng. And let me just make sure that when I've got two screens as well, that I'm seeing everyone here appropriately. So if we could all just give a virtual round of applause to Feng for your good presentation this morning. We really do appreciate it. We do have time for a couple of questions this morning. I think I saw you. Please provide it in the chat if you like, or in keeping with sort of a nice community exchange here, if you want to turn your video on and audio on, you can ask the question yourself. So did I see one from Tal? Was there a question or no? Okay. Does anyone, I see many good boreal thinkers here. Oh, there you go.
I was trying to react, but I raised my hand by mistake. But I did have a question, so I can get us started off. But
perfect.
Yeah, I guess thank you for the presentation. First of all, that was really informative, and I'm looking forward to digging more into your results. I was wondering if there are any particular geographic hotspots that you see emerging across your scenarios that would be like targets for guided protection or restoration efforts?
Yeah. So first of all, this I guess the assumptions related to these all three scenarios are just like one set of assumptions. We're also trying different specifications, different definition of scenarios. So based on this specific scenario definition, we did not presented here. We did try to map those, try to identify those hotspots, those spots experiencing more significant loss historically and shows more like future change, loss of peatland. And one thing I remembered is those oil sand regions really stand out. They are the major loss of peatland areas. And we also see some areas we see a net gain, and but that's mainly outside the oil sand monitoring region. Gain is relatively tiny, and potentially these gain not necessarily actual gain, because really like you forming a peatland takes a long time, but potentially it could be previously got disturbed, and then under, for example, the natural protection scenario, the functioning started to recover, and eventually after 10-20 years you see the recovery turned back to a peatland category, but not like reforming new peatland. It's not quite likely in 20 years you have new peatland growing there. Yeah, but in short, the oil sand monitoring area really stand out.
Thank you for the question and the response. Yeah. Maybe we have one more question here, if that's appropriate.
You can always reach me by email, and
Yes.
Yeah, my team will be very happy to meet with different group, collect feedback. This is an ongoing project. We'd love to hear more back.
Sure. Well, not seeing any right now. However, I know from seeing so many of the names and familiar with many of you on this call, I know there'll be many of you with good questions. And so if you do have those questions, please do either reach out to me directly and I can connect you with Feng, or you will see the presentation on the PHJV YouTube channel. Ian's very fast, probably by this afternoon. So you can access it there and also see Feng's email. But thank you so much for your time. And I'd also encourage too, because this is a more of a boreal group here this morning. And if there are any webinars or topics or information that any of you would like to share with this network, please reach out to me and I'd be happy to try to facilitate that for you. So thank you again, Feng. Look forward to seeing everyone next month and hope you have a wonderful day and we get a little bit of rain all around here. So thank you so much. Take care.
Thank you very much. Bye.
Bye.
Thank you.
All right. Thanks, Ian. I'm going to sign off.
Okay, sounds good.
Take care.